In this section, we're going to be looking at exponential functions. And out of that section, we're going to be evaluating exponential functions. Also evaluate functions that contain base e and use compound interest formulas. We'll first define what an exponential function is. Okay, the exponential function called f with base b is going to be defined by f of x is equal to b to the x or y is equal to b to the x. And in this case, b is going to be a positive constant other than 1. That means that b must be bigger than 0, but it can't be equal to 1. So it's a positive constant other than 1, and your x is going to be any real number. And here's some examples of what exponential functions are. F of x is equal to 2 to the x is an exponential function because it is a positive, the base is a positive constant other than 1, and x is any real number. G of x equals 10 to the x. Here again, that's an exponential function. For the same reason f of x is. H of x is 3 to the exponent of x plus 1. Or 3 to the power of x plus 1. That's an exponential function because in that exponent we do have an x, a variable in it. And the base is a positive constant other than 1. And finally, j of x is equal to 1/2 to the power x minus 1. Now here, 1/2 is a positive constant other than 1. And it's raised to a power that contains a variable in it. Now these are not exponential functions. Capital F of x is equal to x squared. That's not an exponential function because the base is a variable raised to a number. G of x, or capital G of x, equals 1 to the power of x. That too is not an exponential function because by definition an exponential function has to be where the base is a positive constant other than the number 1. And here we got 1 to the x. So that would not qualify as an exponential function. H of x is equal to negative 1 raised to the x. Here the base is a negative number. It has to be a positive constant other than 1. And then capital J of x is equal to x to the x. Here both the base and the exponent are variables. Here the base has to be a positive constant other than 1 raised to a variable. And we can use the graphing calculator to calculate exponential functions. Okay, now let's look at this particular problem here. The exponential function called f of x is equal to 42.2 times 1.56 raised to the x. That models the average amount spent, which is f of x in dollars, at a shopping mall after x hours. You're going to use the exponential function to find the average spent to the nearest dollar after 3 hours in the shopping mall. Okay, now we're going to write down our exponential function that we have here, which is, of course, f of x is equal to 42.2 times 1.56 raised to the x, and here x is equal to 3. Okay. So in this case, we're going to be evaluating f of 3, which means we just replace the x in this exponential function with 3. Okay. Now here's how we can use the graphing calculator to calculate an exponential function. In this case here, we're going to type in the 42.2, and that's multiplied by, and then I'm going to put this in parentheses, 1.56. Now, for the exponent of 3, we can use this key right here, which looks like the upside down V for the exponent, is right below the clear key. So we'll press that and then type in our exponent of 3 and then close the parentheses. And then from here, we just go ahead and hit enter. Okay, now this would be 160.2. I'm not sure what they asked for to the nearest dollar. It'll be $160. Okay. Okay, because this is 160.2, and then it's less. The 2 is less than 5, so we'll leave it as 160. So this will be approximately $160. Okay. So in this case, after 3 hours in a shopping mall, we can assume that the average amount spent would be $160. Okay. So that's how we use our graphing calculator to calculate exponential functions. Okay. All right, the next thing we'll look at is the natural base called e. And the number e is defined as the value such that the quantity of 1 plus 1 over n raised to the power of n approaches as n gets bigger and bigger. So in other words, as the value of n gets bigger and bigger and bigger, the expression 1 plus 1 over n, and that quantity is to the nth power, will be approaching the decimal value of e. And in this case, the decimal value of e will be 2.718281827, and it continues on and on and on. So that's just an approximate value for e. And if you want to access e to the x on your graphing calculator, you'll have to do this. On the TI-83, you have to press second and then LN. That's to get e to the x. So it's always second and LN to get e to the x. And we'll look at a problem that is like that. Here you got the exponential function f of x is equal to 1066 times e to the 0.042x. That problem models the gray wolf population of the western Great Lakes, f of x, x years after 1978. Now here, we want to project the gray wolf population in the recovery area in 2012. Okay, so let me write down the function. And this is for x years after 1978. So here, our x, now we're dealing with the population in 2012. So we'll have to subtract 1978 from 2012. And that would give us 34. So in this case here, x is going to be 34. So what we'll be doing here is evaluating f of 34, which is going to be 1066 times e to the 0.042, and that's going to be multiplied by x, which is 34. Okay, and I'm going to go ahead and put this part right here in parentheses, because I'm going to go ahead and show you how this is done on the calculator. In this case here, we type in our base, which is 1066, times, now for the E, you're going to press the yellow, well, or the blue key, which is your second key, and then LN. Okay. It's second LN to get e to the exponent. And then type in 0.042 times 34 and close the parentheses. And then you're going to hit enter. Okay. Now in this case here, we're going to be rounding this, I believe, to the nearest whole number, which will be 4,446. Okay, so we're looking at approximately 4,446, which is going to be in a whole number. So here, the gray wolf population in that recovery area by 2012 will be 4,446. So here, this is just an example of how you would calculate an exponential function that contains e in it. So to access e, you always press second ln for e to the x. Okay. All right, the next thing we'll look at is compound interest. This is an application of what exponential functions is used. Here, compound interest is nothing but interest compounded on an original investment as well as on any accumulated interest. Okay, so interest, well, compound interest is going to be that interest on top of interest. Well, the interest will be computed on the original investment and also as well as on any accumulated interest. So interest can be compounded in 5 different ways. It can be compounded semi-annually, which means that there are 2 compoundings in a year. If it's compounded quarterly, that means that there are 4 compoundings in a year. Also monthly, meaning that there are 12 compoundings in a year. Daily, now we're going to use n is equal to 365. And then continuous. Okay? And we do have a couple of formulas that deal with compound interest. Okay, and here they are. After t years, t is the number of years, the balance, which is a, in an account with the principal called p, and an annual interest rate, which is r, and r is going to be in decimal form. So usually the interest rate would be given to you as a percent, but you know that you drop the percent sign, move the decimal point 2 places to the left to change it in decimal form. Okay. Now, in this case, the balance is going to be given by the following formulas. If you have n compoundings in a year, whether it's compounded daily or monthly or quarterly or semi-annually, you're going to have to use this formula. A is equal to P times the quantity 1 plus R over N raised to the N times T. And then for continuous compounding, it's the formula A is equal to P times E to the RT. So for continuous compounding, and it will say that in the problem, if it's continuous compounding, you're going to only use this formula. If it's something else other than continuous compounding, you must use this formula here. And let's look at a couple of examples that are like that. A sum of $10,000 is invested at an annual rate of 8%. And here you want to find the balance in the account after 5 years subject to A, quarterly compounding, and B, continuous compounding. Okay, so let's look at what we're given in this particular problem. We're told that a sum of $10,000, that's the principal, is invested at an annual rate of 8%. So R is 8%, but 8% as a decimal will be 0.08. And we want to find the balance in the account after 5 years. So we know T is 5 and is subject to quarterly compounding. So this is part A. Quarterly compounding. If it's compounded quarterly, that means that N is equal to 4. And since we have a compounding that's done quarterly, we must use this formula. A is equal to P times 1 plus r divided by n raised to the n times t. And then we just replace these values in this particular formula to find out what that amount is. A is going to be equal to P is 10,000 multiplied by the quantity of 1 plus R, which is 8%, as a decimal, that's 0.08, divided by N, which is the number of compoundings, that's 4. And then, again, N is 4 and T is 5. So that'd be N times T, or 4 times 5. Now, if I simplify this a little bit, now I will be using the calculator shortly. So here, this will be A is equal to 10,000 times 1 plus. Now I know 0.08 divided by 4. That would give me 0.02. And if I do multiply 4 times 5, that's going to give me 20. Now I can simplify this a little bit more here. So 1 plus 0.02 will be 1.02. So I'm going to have A is equal to 10,000 times 1.02 raised to the 20th power. And here's how we'll calculate this using the calculator. We'll type in 10,000 and then 1 point times, or just the times key, 1.02, and then hit your upside down V, which is a caret key that's below the clear key. It's this key right here that I have on top of my right, where I'm putting my finger above it for the exponent, and then 20, and then hit enter. Now we always round to 2 decimal places because we're dealing with money amounts. So this will be $14,859.47. So the amount the balance in that account after 5 years, subject to quarterly compounding of a $10,000 investment at 8% interest compounded quarterly, would be $14,859.47. All right, so I've done part A. Here's part B. Continuous compounding. Now, for continuous compounding, we always use the formula A is equal to P times e to the RT. Okay, now it's just basically reading the problem. So to determine which formula you're going to have to use. So for continuous compounding, which is what part B says, you have to use this formula. A is equal to P times e to the RT. Now P is 10,000, so we'll have A is equal to P, which is 10,000, times E to the R, which is, in this case, 0.08, times T, which is 5. So here, to calculate this, it's going to be a little bit different here. So here we're going to have 10,000, so we enter 10,000. For the E, you always press second and LN. Again, second and LN for your E to the X. And then we'll type in 0.08 times 5 and close the parentheses. And then hit enter. Now again, we're going to round to 2 decimal places here because we're dealing with money amounts. So this will be $14,918.25. So if this was compounded continuously for 5 years, this will be the amount that will be in that will be the balance in that account of a $10,000 investment at 8% compounded continuously for 5 years $14,918.25. Okay, and that will conclude this particular section on exponential functions.